Ready? Okay, welcome to the last Kent seminar series of this academic year. And we don't have it next week, which is reading day, and we do have a presentation on campus, if you don't know that already. It'd be at the NCSA building. It's the Illinois Secretary of Transportation, Ann Schneider. She'll be presenting from 4 to 5 in the big NCSA auditorium. So be sure to be there, hear about that. She's going to actually talk about transportation sustainability. That's the general topic. Today we're going to have a presentation by Ryan Smith and Eric Fairby. They'll be talking about some work they started last semester related to optimizing staging area locations and material recycling. And both Eric and Ryan are undergrads here in the Transportation Civil Engineering Department, and they're both getting the master's. This work was done in collaboration with Professor Oyang, who's Ryan's advisor, and I'm Eric's advisor. So hopefully you'll enjoy the presentation. It has some implications for some of the projects on what people are working on in this room. So let's welcome Ryan and Eric.
Thank you. So to start off, so I'm here to present the optimal staging area locations and material recycling strategies for sustainable highway reconstruction. As Professor Raessler mentioned, with Eric, Professor Oyang, and Professor Raessler. To start off, just give you some outline. We're going to go over an introduction, then go over the model formulation, go over the case study of I-90, and finally a conclusion and future study. So we've all seen roads like this. We've all been driving, see road work ahead signs. Construction on highways is going to continue to happen, and it is necessary for continuing improvement of our infrastructure. But when this happens, there's a lot of material movement. There's a lot of decisions that need to be made. There's a lot of energy and emissions that are associated with this. And our question is, how can we optimize the reconstruction? So some of the renewal options are repaving, resurfacing, or full reconstruction. We want to focus mostly on full reconstruction, mostly because it's the most difficult and most complex. The reason why it's the most complex and most difficult is because the most material is moved. Instead of just tearing up one layer of the road and putting it down, we have to tear up the full road. So our questions are, how to best utilize the material in the existing roadway? When they tear up this material and they put it in a truck, where does that truck go? Where should it go? Another question is, how do we satisfy this demand of the future roadway? We could potentially recycle this material that we tear up from the original roadway, from the existing roadway, to satisfy some of this demand. Other questions are, how do we balance the costs and environmental concerns? Some of the environmental concerns, maybe we want to limit the amount of solid waste, CO2, or energy. This project is actually part of a larger project that actually Eric is on called Roadway Life Cycle Assessment.
So as Ryan mentioned, we started this life cycle assessment tool last fall, and to give you guys a brief background on it, life cycle assessment basically has 5 phases: a materials phase, a construction phase, a maintenance and rehabilitation phase, use phase, and end of life phase. Well, this project falls kind of in here with some within some of these phases, and it's not like an entire life cycle assessment, but basically what we're focusing on is the construction and part of the end of life phase as we're tearing up a road and then reusing it in the construction phase. So it's a very complicated part of the life cycle assessment tool that we're using different aspects of it to try and quantify the emissions, energy usage, and kind of cost of what all of this means and how we can optimize it.
So to give you an introduction about some of the objectives and criteria that you can have for sustainable highway construction. You could design a reconstruction plan just for longer life. Maybe you want to reduce the rehab, users delay, emissions associated with having to reconstruct a road multiple times. You can have safety and society concerns. You can reduce the noise or splash, improve the safety. One of the big ones is construction. Maybe you want to minimize the effect of construction delay on users, or you can minimize the material transportation. As I mentioned earlier, material transportation is a huge problem, and it's a huge question that we need to solve just because of the amount of material that is being moved during these projects. Lastly, you can have environmental concerns and objectives, such as maximizing the amount of recycled material that you use in the future roadway, or the new roadway that is being planned. You can minimize the amount of solid waste transported to landfills, energy, and emissions as well. The three that we're going to focus on is material transportation, energy emissions, or energy consumption, and CO2 emissions. Now this is similar to this is the same picture Eric talked about, but what we're focusing on is the end of life. The question on how we take the material at the end of life and how do we take it to different locations. One of the potential locations we can take this is we can sell this material back to the market. This may require us to transport it to the markets, but maybe we can gain some profit from selling it to them. We could take this recycled material and take it back to a field process, or we could take it back to a plant process. In our model, both of these are the same thing. They're a processing area. What happens in a processing area is this material can then gets reprocessed so that you can reuse it in the new pavement. The processing areas in our model, there's two types. There's fixed processing areas and there's mobile processing units. A fixed processing area, these are typically what you'd see if you're going on the highway and there's a big road construction project. They're fixed locations. They have a lot of machinery, a lot of storage, a lot of machinery to process material. Mobile processors are a lot smaller. They may only be used to process a subset of all your materials. But the goal with them is maybe you don't have to transport material to these fixed processing areas. Maybe you can just do it in place. To give you an overview of the model a little more, so if this is our existing roadway, and over time we're going to have construction, so we tear up the entire roadway, and we end up with the new roadway at the end. There's multiple locations in this model. We have landfills, we have markets, we have the fixed processing areas, and we have the mobile processing units. Our question is, how do we take the material from this existing roadway and transport it to all these locations? Which locations do we transport it to is an additional question. How do we take material that we purchase from the market and send it to the processing areas so that we can use it in the final roadway? In fact, how we take that material from the processing areas to the final roadway to satisfy the demand. There's very little literature on just facility and recycling strategies for highway reconstruction. Thanks to Young-Jae Xiao, we have some forest road literature that is similar in that with this literature, they wanted to have forest roads that are of temporary use. You tend to only use them for a certain amount of time to harvest wood, for instance, and then you decommission the road. So the Thompson and Sessions papers with product movement and material recycling, they allow for you to decommission roads, and when you decommission roads, you can reuse the material from those roads in new roads to harvest more wood in a different location. And then in the Thompson and Sessions 2010 papers, in this, they start looking at multi-criteria objectives. This is interesting because we can look at the same approach. They look at environmental concerns. Maybe if they install a new road, it changes the water runoff pattern and changes the environment in that area, the complete ecosystem change. So we can do similar things if we look at emissions or CO2 only. Now we'll go over the model formulation. So this is a typical plan view of a road. For our model, we have to discretize this segment, or this entire road, into segments. The reason we do this is instead of looking at a macroscopic approach of just looking at the entire roadway as one source of demand and supply, we now start looking at just a little portion of that area as a location of supply and demand. The other reason is if we look at a profile view of the road, right, the pavement design could change over the length of the road. If the pavement design changes, we need to have the separation between segments be at this point. The reason why is because we have a certain supply and demand that's associated with each layer in each segment. As the layers change, maybe the pavement design changes, the supply and demand of material is going to change. To kind of give you a better view, this is for the I-90 case study, which we'll explain later, go over later. This is the existing roadway configuration. So there's hot mix asphalt, then we got some concrete and a granular base. Now each one of these locations has a certain supply of material. We define the supply material for each segment and then for each layer. So this would be one layer, this would be another. The shoulders are not shown in this. That is an additional layer. It's just the location of where the supply and demand is. And then you can see for the proposed configuration, we have a concrete top, but it's not uniform throughout the entire 12-inch layer. So we had to break this up into two layers because each layer also needs to have uniform design. So the virgin concrete layer has a uniform design of supply and demand, and then the same thing is similar with the 9-inch frap version of the concrete. So there's a lot of sets and a lot of parameters in our model. To briefly go over some of these, we have some sets to just define the construction. So we have all the time periods for construction, all the layers, all the segments. We have some sets describing the types of materials that you can use and where you can use them. And then we have a lot of locations, so the markets, the landfills, and all the candidate locations for processing areas. Based on the pavement design, we have supply and demand at every location. The other interesting thing from the pavement design is we have the max portion of demand that can be satisfied from recycled sources. So we limit how much recycled material that we can use in any particular location. We have more parameters on market information, such as how much does it cost to purchase material from the market and how much you can sell it to the market. And finally, we need to know the distance from every location to every other location. We're going to be transporting this material throughout the network, so knowing the distances is very important. Additionally, we have parameters on the processing areas. So we have some fixed investment costs. We have a processing capacity, a storage capacity of material at each location. We also have energy and emissions data. So we know how much energy and emissions it takes to use a certain type of material in every layer. Finally, we have some cost data. How much cost it is to use 1 unit of energy, how much cost it is for 1 unit of CO2 that's released, and then how much it costs to ship 1 unit of material.
Can we ask questions?
Yeah.
How do you define the energy or emissions to use type M material, for example? Does this include all the way from the production, construction?
So currently one of the issues we have is we don't have some of the data going back. For instance, on the virgin aggregate, we don't have it before it's at the market, so we don't have it's the beginning of its life. For the recycled material, we have it going back to when it gets dug up from the existing roadway. It's one of the things that we're looking to add more into the future work. it's one of the challenging things to acquire all this data. So we have some variables. The first variable is just a decision: where do you locate processing areas? Whether you build one or you don't build one, those are the decisions. Next, we have a lot of variables that are just on how the material flows through the network. So, and the last one, the material storage. At each location, you have the potential to store material. How much material is stored, how much, and then the other variables, how does that material gets distributed throughout the network. So to give you kind of a view of what each variable represents, so X kind of represents how the material is taken from the existing roadway and how it's taken to the landfills, the markets, the processing areas. Y represents the material that you purchase from the market, and that can only be transported to the processing areas or the mobile processing units. And then finally, Z describes how the material reaches the final roadway. So here's our objective, and our objective is to has multiple parts. The first part is we want to minimize the processing area investment. If you open a processing area, it's going to cost you money. So we're trying to weight how many processing areas we should open. We have the market material costs. So if we purchase material from the market, we're going to have to pay for that material, and we're also going to have to transport that material to the site. For the existing roadway, we have the potential to sell that material to the market, but we also, for the material that isn't sold in the market, we have to transport it to a staging area, to a processing area, and that's going to cost us some money. Additionally, if we transport it to a market, it may also cost us money to transport it to that market. Finally, taking the material that's at the processing areas and taking it to the site, this will also cost money just to transport this material. As I explained before, so WJ is just if location J is open, which is just if the processing area is open, and the rest of them are non-negativity constraints. So the flow has to be positive. We don't allow any flow to go backwards. Additionally, so we have some other constraints. The previous roadway supplies some material. We have to send this material somewhere. We can't just leave it on the side of the road. So we have a constraint enforcing that. When material goes to a processing area, the inflow of material to that processing area and the outflow of material from that processing area has to be equal. At the end of the day, we still don't want material just sitting there. And finally, when we have the new roadway has some demand of material, we need to make sure that we satisfy this demand. As I mentioned earlier, we can only have up to a certain limit that it comes from recycled sources. So we enforce that the amount of recycled material that's getting shipped to any particular location, that is a segment and a layer, is less than what we specify. At every processing area location, we can only store so much material. So we have a constraint for that. And additionally, at every staging area location, we can only process so much material. So we have a constraint limiting how much we can process. One thing about this last portion, as you'll see in the case study, this constraint, it doesn't really take effect because it's really the transportation costs and the transportation distance that really wants you to open up new staging areas or new processing areas. It's not that we've reached our limit on any processing area. To talk about the I-90 case study, so this is the northwest part of Chicago between Rockford and pretty much O'Hare. It's called the Rebuilding and Widening Project. It's part of a $12 billion capital program, Move Illinois, the Illinois Tollway Driving the Future. Some details about this project. in between these two spots, it exists, right now there's only 2 lanes. They're expanding this to 3 lanes in each direction. And between here and here, I think O'Hare is somewhere around here, they're expanding it to 4 lanes. Since they're expanding this roadway, they have to completely tear up and do reconstruction. They have stated that they want to build green. They want to minimize the environmental impact of construction. And they want to do this by reusing, and recycling as much material as possible. They've even stated that the entire existing pavement will be recycled into the new pavement. So to give you some background on how much data there actually is in this problem is, first we split up, it's a 35-mile stretch of roadway. So in each direction, we split up it into 3.5-mile segments. So there are 20 segments for our problem. There are 4 layers in the existing pavement, as I showed you before. The shoulders are not shown, and then 7 layers in the new pavement. There's 2 layers in the shoulders for the new pavement. There were 16 candidate locations for fixed processing areas. The tollway owns 4 of them currently, so these could be the interchange, kind of the area around those. The tollway owns that land, thus wouldn't have to pay anything for it. The rest of the locations, and like the rest of the data, was very generously, the tollway helped us out a lot with that, so thanks to them. We considered every segment as a potential candidate location for mobile processing units. So wherever we want to put a mobile processor, we can do it. There are also 16 markets. Now, each one of these markets doesn't necessarily sell and supply or buy and sell all types of materials. They only buy and sell particular sets of materials. So you may have an asphalt or an asphalt company that sells mainly just asphalt goods, and a concrete company that just mainly sells concrete goods. So the locations of these are important as well. Now, there was no data that we had on landfill locations, so we had to assume that there would be at least one landfill in the general area. So we just made an assumption that every segment could reach a landfill in a certain distance. Now, we had other requirements, as I specified before. We need to know the supply and demand based on the pavement design. And we need to have this specified for each segment and each layer. Well, each layer in each segment. We need to know the location information for every single one of these points. So where the existing roadway is, where the roadway is, where are all the candidate locations, and where are the markets, where are the landfills. Finally, to start getting into the energy and emissions, we need to know the construction equipment productivity to determine some of that. We also just need to know the market costs. Now, we wanted to answer a few particular questions for this case study. One of them was, which processing areas should be in operation? Another was, what is the optimal recycling material processing strategy? So how do we take material from the existing roadway, and where do we take it to? How should material be purchased from the markets? And finally, how is material transported from the processing areas to the demand sites? So we wanted to make a comparison between 2 scenarios to give a better explanation. Our first scenario, we only used the 4 processing areas that were owned by the tollway. This way, we still ran the model, but we forced the solution to only use these four processing areas since they were free. Our second one is we would minimize facility, material, transportation, energy, and emissions costs, and find out what are the optimal locations for processing areas, and what is the optimal material flow strategy. So to give you some background, This is the eastbound direction of I-90. This would be the westbound direction of I-90. Each one of these blue squares is a potential candidate location for a fixed processing area. Each one of these triangles is a market location. And as I mentioned before, not all the markets sell all types of materials. This diamond up here, this is the one landfill that we assumed for this project. And additionally, they're hard to see, but there's like a red X in the middle of each one of these segments. Those are candidate locations for in-place processing units. We also assume that all the transportation will occur from the center of each segment. So to answer which processing areas should be in operation. So scenario one, these were the four processing areas that the tollway owns. If you can see when we ran our model and we found the solution, we found it was much different. So we increased the number of fixed processing areas by 2, so we got a total of 6. You can still see that we're still using the 4 that are free, but we added 2 additional fixed processing areas. In addition to that, the model put out that we were using 9 mobile processing units. So you can see 1, 2, 3. All of these are mobile processing units. The reason why it shifts more to using more processing areas should become clear by the end. So to determine what is the optimal recycled material processing strategy. So this is how material moves from the existing roadway and where does it go to. So it's only how the material flows out of the existing roadway. So for instance, in this case, you can see that the thickness of the line also represents how much material is being moved. So you can see from this segment, a lot of the material is being moved to this staging area. Similarly, some of this material is getting transported to markets, so it's getting sold to the markets for profit. And then even more, some of this material is getting transported to the landfill. Whether it's just more cost efficient to take it to the landfill, or there's no use for this material. Either one is possible. As you can see in our optimal solution, the lines are significantly less thick, mostly because there's significantly more in-place processing units. So material that is processed in place doesn't have to be transported anywhere. It just happens directly where it's dug up. So this is how material is purchased from the markets and where it is transported to. This goes back to how not all markets sell all type of materials. So I don't have the labels on each one of these, but there are some parts that needed asphalt material, some that needed just aggregate. So for instance, maybe this is the asphalt market and it needs to distribute its products or its materials to all the staging areas so that they can satisfy the demand in the end for the new pavement. You can see that in this one, there's less staging areas or less processing areas, so a lot more material is being shipped to particular locations. In our solution, we also assumed that an in-place processing unit didn't have the capacity to receive shipments from the market. So any material that was bought from the market had to go to a fixed processing area. So this is how material is moved from the processing area to the new roadway. As you can see in this model, a lot of material needed to be moved back because there were no in-place processing units. And additionally, there were some processing areas that were serving distances the whole way. So this is 35 miles, so about 35 miles away. Where in our solution, each staging area is really locating on just the areas closest to them. To show some results, So scenario 1, we only had 4 total processing areas. All of them were fixed. In scenario 2, we had 15. 6 were fixed, 9 were mobile. We calculated the total material movement for each group, for all material, for just the recycled material, and just the virgin material. You can see by opening more processing areas, we can decrease the total amount of material movements. It's more interesting that it can significantly reduce the amount of material or ton miles for just recycled materials. If you think about this, whenever we open more and we open more mobile processing units, none of that material is shipped anywhere. It is done in place. So this can significantly make reductions in the amount of recycled ton miles. Whereas with virgin material, we still saw a reduction, but the reduction is nowhere near as much because these markets are located much farther away. By opening another processing area, you're only decreasing maybe the last few miles of the trip where it may have already have traveled over 50 miles or however far away the market was. That's why you see a significant or not as small of a reduction in virgin material. So on to the conclusion. So as the results on the last page show, as material recycling becomes more important, much more attention must be given to processing area locations. It can significantly reduce the amount of ton miles for recycled materials. One thing that we did in this model and for our case study is we only assumed a single type of pavement design. What we'd like to do is compare this with a different pavement design. So we compare the concrete roadway design with a just hot mix asphalt roadway design. Then compare how the processing area locations and how the material flow are going to differ. Finally, we'd like to integrate this model with the bigger model that Eric is working on, the roadway life cycle assessment tool. That is it. That was very fast.
Any questions?
Yeah.
Yeah, I have a question. Would you consider a analysis, like if the location were slightly moved a mile?
No, we would like to do it in the future, though. This is still just ongoing work. We've really been trying to hack it out. There's so much data that we've had to acquire. That's really been the big thing that's holding us back. Sensitivity analysis.
Where the staging areas would be.
I will say, at least with the mobile processing areas, since you're driving on the highway, the other direction is not that far away from you. So having a mobile processing unit on that side of the road or on your side of the road isn't going to make a large difference. So I would assume that if you're looking at the mobile processing units, the sensitivity analysis could really, it could really fluctuate, at least the solution. Yep.
Is the tollway using this now?
No. They, at least from my understanding, they aren't.
It's very, very interesting. We are also part of this life cycle business team, and then it's really nice to look at the problem from a different perspective. I really like the work and then the presentation today. Just a quick question. Having, let's say, 9 mobile plants, is this, do you think, feasible for many of the contractors? Can they really put up so many mobile plants? Have you ever thought about this?
That is a good question. So we focus more on the overall agency planning, not necessarily as a contractor, how we would approach it. Because really the overall agency can say, hey, we will only allow you to bid on this project if you use this many mobile processors. Or if you're looking at the construction standpoint, it's probably not feasible. But the other thing that's interesting is this project is over 2 years. All right, they're doing one direction completely. not all the road is going to be dug up at the same time. So maybe you have a mobile processor, but you move it. We didn't consider moving a mobile processor. We just said there would be one in use at this location. If you want to get more into like a construction scheduling problem, you could maybe move some of those mobile processors from time period to time period, and then you would get a reduction in the total number you need.
No, I think to follow up though, I mean, one of the strategies is certain segments should use mobile processing as they bid the contract, and other segments you should bid as staging areas because of the location.
Another big aspect of this, if you have so many, let's say you're able to have so many mobile plants and which might be working at a smaller capacity. Now, one of the things that we have experienced, and then we know that the efficiency of those plants is you produce less, then it reduces. So you might be actually increasing your energy and efficiency if you use smaller and smaller plants. So it's sometimes good to have a big plant in terms of construction, in terms of emissions and energy during the production, not transportation.
Yeah. Then
you can, of course, suffer from transporting those materials to the job site. So there is another trade-off with working with the small plants, small and mobile plants especially.
An additional issue on that is that if the problem is really geared by transportation costs are by far the largest cost. At least with the CO2 tax that we have seen, it's not going to make a drastic impact on, oh, we should definitely do this project or do it this way over how we were just designing for transportation. And additionally, transportation, energy, and emission, if you decrease the number of ton miles, you're going to have a better solution or a cheaper solution.
They're competing.
Yeah.
Transportation and the plant energies, they are competing. Within the service life of the payment, they are minimal, honestly.
Yeah.
Like in total, 5% of the total energy and emissions during the service life of that payment, for example, I-90 that you're working on. But mobile versus stationary plants, there can be some significant difference. Plus, mobile plants, for example, is not an option for asphalt production, for example.
Yeah. Well, additionally, so at least in our model, if you wanted to go an approach where we only allowed particular types of materials to be processed at in-place processing units. So really the only thing we used it for was whenever one of our layers was the crushed concrete layer. They crushed that and then instantly just put it back as the base layer in the new roadway. That was the only material that we actually allowed to go through that process. So you have that ability that if you want to not allow everything just to be in place, because you could increase the emissions and energy significantly.
Yeah, so we can add a lot of constraints additional when we are defining the problem. Some flows we force them to be zero, just like what Ryan was saying. Essentially, you force that to be zero, and also the mobile versus fixed. We can assign different costs. And also different impacts in terms of the emission and everything. We do have some terms in the objective to capture the emission from each location.
That's part of the data we are collecting now. We really want to understand how those plants work, stationary versus mobile, their efficiency, and the effect of being mobile or efficiency, how much will it impact on the emissions and energy.
Right. Yeah. So the data is we are still collecting the data, yes, we all know that. But then the model has the flexibility to accommodate those ones once data becomes available.
We usually allow, so whenever you use a type of material, depending on where it goes to, you can put in different emissions and energies. So if you're sending that material to a fixed processing location, you can put in a smaller emission and energy compared to if you were using it at a mobile. And also where it ends up being used in the final roadway. That may have some effect on the energy and emissions as well.
More questions? Should we ask some questions?
Yeah, actually, I would like to make a comment on the sensitivity analysis. Actually, I think Ryan and Eric, you guys did some sensitivity about in earlier work about some other things, not necessarily about the location of the plant or the staging areas, but rather about, for example, some policy making decisions, such as there's a percentage limit on the recycled material as a percentage in overall material in new payment. This is actually obvious as mechanical reasons that we want to limit that recycled material. We don't want to degrade the quality. But then the question is how much is too much? Then in terms of the impact into the quality. So on one side, mechanistically, we understand the performance of the pavement under different percentage of recycled materials. But this model would allow us to answer the question, how much is the economic impact? How much is the environmental impact? How much recycled material can be absorbed into the new road? So this model will allow us to address those questions. So that is the sensitivity analysis actually we worked on already, but we just didn't show it today.
The reason being is that really needs to be implemented into the larger model, or the bigger overview project, because that one we can't determine how much maintenance or construction, what's the life cycle for that future roadway based on how much recycled material. We use it as just an input, and we say you can use this much. But really, it's what Eric is working on that will be. So if we use this much recycled material, what is our life cycle assessment? And that's why they need to kind of be integrated.
Okay, thanks.
Thank you.
Good presentation.